That was a building in Beirut in 2026 after a missile attack. It shows a hidden problem that often goes unnoticed. Leaving it unfixed will cost us dearly. In 2023, a single earthquake in Turkey destroyed 160,000 buildings in seconds. In Syria, 8 years of conflict destroyed 900,000. War in Ukraine, disaster in Haiti and Nepal. Across just 5 major disasters, nearly 2.5 million buildings collapsed. That is roughly 58 million tons of shattered concrete, twisted steel, and broken stone. Most of that rubble is treated as waste, but inside a broken concrete, there's something that we can use as a solution to our climate problem. But how comes destruction is a solution? This is where one idea begins: carbonated, recycled concrete aggregate. To understand why that matters, we need to look back to where concrete starts: the cement kiln. Making cement means heating limestone and clay to 1,450 degrees Celsius. This process, called calcination, cracks limestone apart, releases carbon dioxide, and becomes a clinker. Cement production alone is responsible for 7 to 8% of all global carbon dioxide emissions. That is more than aviation and shipping combined. Now let's go back to the rubble. Instead of borrowing the demolished concrete, we can recover it. When demolished concrete is crushed, sorted through screens, and cleared of steel with magnets, it becomes recycled concrete aggregate, or as known as RCA. The old concrete gets a second life as the gravel inside new concrete. Cleaner and coarse fractions are recycled into new concrete, and the lower quality fractions are used for other concrete-based goods. From those 5 disaster sites, we could recover 21 million tons of usable RCA. That's enough to reconstruct nearly 100,000 new buildings. But RCA has a weakness. Residual mortar stays attached to its surface, making it more porous, more absorbent, and weaker than natural aggregate. The important part is this: that old mortar still contains calcium hydroxide, so the weakness also becomes the reaction site. This is where RCA and carbon capture combine. The carbon dioxide released earlier by the cement can be sent back into the recovered concrete. When carbon dioxide enters moist residual mortar, carbonation happens. Calcium hydroxide reacts with carbon dioxide to form calcium carbonate, or as known as CaCO3 plus water. The calcium carbonate, or limestone, act like a natural filler. They plug up tiny holes and pack the weak spots tightly, making the material much denser. Instead of the gas escaping back into the air, it gets trapped and turned into solid minerals inside the recycled concrete aggregate. This makes the surface stronger, keeps water out, and results in what we call carbonated RCA. So this is not 2 separate ideas. It is one simple loop. Recover the RCA, cure it with carbon dioxide, then reuse it in new concrete. Our innovation takes this natural reaction and engineers it across 3 strategic injection points. Phase 1 is recovery and preparation. Rubble is crushed, cleaned, and graded, so the old mortar on RCA is exposed and ready to react. Phase 2, carbon dioxide curing. In a controlled chamber or curing environment, carbon dioxide diffuses into that mortar and forms calcium carbonate inside the pores. Phase 3 is reuse. The carbonated RCA returns to new concrete with lower porosity and stronger bonding potential. After its service life ends, the cycle can begin again. But does it work? A life cycle assessment study conducted in Singapore shows this process achieves negative 21.42 kilograms of CO2 equivalent per ton of RCA. This is carbon negative concrete. On global scale, this approach could deliver up to 0.64 gigatons of carbon dioxide equivalent reduction per year globally, contributing equivalent to 10 until 35% of the Paris Agreement's negative emission target. This is not a magic fix though. Carbon dioxide curing raises costs by 4 to 14%. Each phase demands precise control of moisture, pressure, and timing, and carbonation lowers pH levels, risking steel corrosion without protective measures. So the goal is not to use the carbon dioxide carelessly. The goal is to use it precisely, where the material design, curing conditions, and durability protection are all engineered together. Most people see waste. We see 21 million tons of aggregate waiting to capture carbon and become something stronger. And the carbon dioxide leaving the kiln does not have to stay a problem. Carbonated RCA brings the two storylines together. Rubber provides the material and captured carbon provides the cure. One waste stream helps repair another. Not all innovations are new. Some are rebuilt from what we leave behind. Thank you.